Hello everyone, hope you are doing well. I am Reza, founder of the optimizationcity.com. In this website, we find all you need in subject of the operation research, including documents, video, online server, reference book, online calculator, and other things. At the end of this presentation, I will introduce you a little bit more about this website. So let's get back to learn LP. In the first course, I'm going to learn the basic of operations research, which is linear programming. Before we dive into the detail, let me give you an overview of what we will be covering today. Here is a table of content of our course. Firstly, we will be discussing what operation research is, and we will be exploring the history and the key concept of the operation research. Secondly, we will be discussing about formulating the linear programming, and we discuss the basic step involved in formulation of LP. Thirdly, we will be discussing the math representation of linear programming. We will be explore the various mathematical notation and symbol used in LP. Fourthly, we will be discussing the key terms used in LP, such as decision variable, objective function, constraint, feasible region, and optimal solution. Fifthly, we will be discussing the classification of the linear programming. LP can be classified into the different category based on the structure and characteristic. Finally, we will be doing exercise to put our knowledge of linear programming in the problem. So let's get started. What is operation research? Operation research, in abbreviation OR, is a scientific approach to making a decision in organized system. It's used to guide and coordinate activity in various fields such as economics, trade, industry, government, health, and more. With a systematic approach, operation research aims to solve conflict between different parts of the organization and find the best solution for entire organization. Operations research covers several areas, and one of the most critical area is linear programming. In this approach, we use a mathematical model to explain the problem where our mathematical relation must be linear. LP was first introduced in 1947 when George Dantzig invented the simplex method, a way to solve the general linear programming problems. His invention was so important in management science. Dantzig was even nominated for Nobel Prize, although he never won it. During the World War II, OR played a critical role in military and decision making. The military faced complex and challenging problems such as determining the most effective way to deploy troops and supply, minimizing casualties, subject to limited resources. To address this challenge, the military turned to OR, which was a relatively new field at that time. Okay, let's move on a small example of LP in this section. This is actually simple enough that we can study it graphically. Consider a company that makes door and windows, has 3 plants. Each plant produces a different part of the products. The manager wants to introduce 2 new products and has asked the Operation Research Center to increase production based on a plant's capacity. The 2 new products are a door with an aluminum frame and a glass window with a woven frame. Plant 3 is required for both products, so its capacity will determine which product get priority. Here there is a table that this is a table that we all information we need. This is the table we need. In this table, product one in this table show that product one use 1 unit of plants one capacity and no capacity from plant two. It used 2 unit of plants three capacity. Product two does not use any plants one capacity, but it used 2 unit of plants two capacity and 2 units of plants three capacity. The profit per unit for product one is 3 and for product two is 5. The capacity of plants 1, 2, 3 is 4, 12, and 18 respectively. We use x1 and x2 to represent the number of products 1 and 2 produced per hour respectively. The profit from sale per hour is represented as Z. In operation research, x1 and x2 are known as a decision variable and Z is referred to as an objective function. We want to maximize the profit, so the objective function is sum of the profit from both products, which is 3x1 plus 5x2. To produce 1 unit of product 1, we need 1 unit of plants 1, which has a capacity of 4 units per hour. This constraint is expressed as x1 less than 4. Similarly, for plant 2, this is plant 2, the limit for product 2 is 2x2 less than 12. The both product use plant 3 capacity, which is shown 3x1 plus 2x2 less than 18. Since the products cannot be negative, we set the decision variable to be non-negative, which are x1 equal or greater than 0 and x2 equal or greater than 0. Here is a summary of the mathematical representative of the LP model for the example. We use a graphical method to solve this LP model because it only has two variables, x1 and x2. First, we draw a graph with x1 and x2 axes. Then we add each constraint to create a feasible region. This region is where all constraints overlap. Finally, we identify the point within the feasible region that produce maximum value of profit, which is called objective function. This is the optimal solution of this problem. In this point, we have the maximum value of the objective function, which is 36. Therefore, by producing 2 units of product 1 and 6 units of product 2, the most revenue 36 per hour is generated. We generalize the problem of the door and window manufacturing company in this section. The problem involves 3 plants with the limited capacity that 2 products need to use. In general form, we want to assign M source to N competing products. We use xj to represent amount of product j and z to represent the measure of effectiveness due to each unit increase of xj. This is the measure of effectiveness for each unit of increase product 1, product 2 till product n. bi is the amount of source I, b1 until bm, and aij is the amount of source I consumed by product j. Here is the summary of the information in the table below. We need to solve the linear programming. For the problem, it's called resource allocation problem. Okay, this is the mathematical representation of the resource allocation problem that's shown in this slide. To simplify, expressing problem in LP, here are some common words and their definition. The objective function is a function c1 x1 plus c2 x2 plus till cn xn that aim to find the maximum value. A functional constraint is a function that shows the total resource consumption for all product. The non-negative constraint is xj greater than 0. A constraint is a set of functional constraint and non-negative constraint. A decision variable indicates the amount of each product, and finally a parameters refer to data we need to solve the problem that is fixed and constant. Note that the standard model may differ from the linear programming model in reality. There are alternative form of linear programming that can be converted to the standard form, including min instead of max objective function, functional constraints that are used greater than or equal, and constraints that use equality, and the variable that are only negative or unrestricted in sign, either negative or positive. In short, more common term in the linear programming. In short, a solution denotes a set of value given to the decision variable x1, x2 until xn. For instance, in the previous example, the point 2, 3, and 5, 5 represent the solution of the LP, regardless of whether they fall within or outside of the feasible region. What is feasible region? In short, feasible region is a solution that satisfies all constraints, including functional and non-negative constraints. For instance, in the illustrated example here, point 2 is a feasible solution, whereas the solution 5, 5 is not feasible. It's out of the feasible region that's called infeasible region. What is optimal solution? In brief, an optimal solution is a feasible solution that yields the most desirable value for the objective function. Figure below shows that the optimal solution for the previous example is this point. This point is most wanted value of the objective function for all value in this feasible solution. There are 4 possibility scenarios for the optimal solution. One is unique optimal solution. In this case, there is only one feasible point that represents the optimal solution, as shown in the figure above here. Multiple optimal solution, what is this? While most linear program problems have only one solution, this is not always true. In the previous example, if revenue of product 2 decreased from 5 to 2, the objective function line becomes parallel to the line 3x1 plus 2x2 equal 18, resulting in a range of the optimal solution. Align the line between 2, 6 and 4, 3 points. This is the line between these 2 points, and all points in this line will be optimal solution. It's called multiple optimal solution. An unbounded solution arises when the constraint fail to limit the objective function z from increasing infinitely in a desired direction. In previous example, if we remove the both constraint 2x2 less than 12 and 3x1 plus 2x2 less than 18, the feasible region expands, allowing the objective function value to increase infinitely in the direction of the feasible space that's shown in this figure. What is the infeasible solution? An infeasible solution occurs when the problem has no feasible solution or when the feasible region is empty. For instance, in the previous example, if we change the constraint to x2 less than 12 to x2 greater than 12, and the constraint x1 less than 4 changed to x1 greater than 4, the feasible region become empty, resulting in no solution for the problem. In summary, the the possible scenario for the optimal solution are unique optimal solution, multiple optimal solution, unbounded solution, and infeasible solution. Additionally, there is a phenomenon called degeneracy, which occur in two variable problem when a kernel point of the intersection of more than two constraints is present. This issue can be raised in n variable problem. To show this problem, consider the following example. This problem has two variables and two constraints. As it's shown here, in this problem, we observe that the three corner points coincide at point A, which are intersection point of first constraint and axis and x2 axis. The second intersection is for second constraint and x2 axis, and the intersection point of the two constraints. In the simplex method we will discuss in the next course, each iteration represents a characteristic of each corner. When several corner points coincide in degeneracy, we may encounter a situation where successive iterations occur on this point. It's called degeneracy. We will discuss in future more about this. That's shown in this slide. So, linear programming can be classified into various types based on a possible situation for the optimal solution. Previous section discussed some specific case of the linear programming. Generally, these types include in this figure. We can summarize what we discussed before. In this figure, we illustrate the various possible cases that occur in the feasible region of the two variable linear program. That will be very important to understand the different classification based on feasible region. Okay, in the linear programming, constraint can be classified in two groups based on the effective on the feasible region and the optimal solution. So we have two type of constraints based on the effect of constraint on the optimal solution. First, effective constraints. These constraints play the critical role in forming the feasible region. Adding any new effective constraint reduces the feasible region, while removing an effective constraint increases the feasible region. Redundant constraint. These constraints do not impact the formation of the feasible region. Their present or absent does not alter the feasible region. We have the example you can see here. Consider the following problem as an example. Its graphical representation is depicted below. We have three constraints and two variables. It's worth noting that only the first constraint and non-negativity constraint are relevant to forming the feasible solution. That's called effective constraint. Rather, the second and third constraint do not contribute to the creating the feasible region and also determining the optimal solution. So these two constraints are redundant. Consider the following example. There is an area consisting of the three farms and two constraints, land and water, that restrict the agricultural possibility of these farms. The table below provides information about the water allocation and usable land of these farms. This region is suitable for cultivating crops such as the sugar beet, cotton, and sorghum. These crops vary in their expected net return or profit per acre and water usage. Additionally, there is a maximum limit on the acre that can be allocated to each crops. Is shown in this table. Here, this is the figure of the cotton, sorghum, and sugar beet is a very popular crops in the farming industry. To maintain fairness among these three farms, it has been decided that each farmer has to allocate the same proportion of their available land for planting. For instance, if farm 1 plants 200 of this available 400 acres, then farm 2 must plant 300 of its 600 acres. And while farm 3 plants 150 acre of its 300 acre. However, any combination of crops can be grown on any of farms. The task is to determine how many acres of each crops should be allocated to each farm while adhering to a given constraint. The objective is to maximize the overall net return. How we can solve this problem? We will formulate this problem as a linear programming model. The decision variable in this problem are the number of acres to allocate each of these three crops at each of the three farms. Decision variables are as follows, which is shown in this table. For example, in the table mentioned here, x1 represent the number of acres on farm 1 for the sugar beets. We have 9 decision variables. As the objective function, which is shown as z, aims to maximize the net return. The problem is subject to following constraint, which is stated as before. For the usable land for each farm, we have the three constraints for farm 1, farm 2, and farm 3. For allocation water for each farm, we have three constraints for this constraint. We have, for example, for farm 1, 3x1 plus 2x4 plus x7 is less than 600 and so forth. And for total acre for each crops, which has the limitation for each crops. For crops 1, we have 600 limitation acre, which is shown is x1 plus x2 plus x3 is less than 600 and so forth. The problem also includes the following constraint to ensure an equal proportion of the land is planted on each farm. It's the fairness limitation, which is stated in the problem. Equality of cultivated land to a usable land for farm 1 and farm 2, which is shown here. Equality of cultivated land to usable land for farm 1 and farm 3. Equality of cultivated land to usable land for farm 2 and farm 3, which is shown here. The above initially, these constraints are not in the suitable form of the linear programming, as some of the variables are on the right-hand side, which is not a standard in the linear math representation. Thus, their final form can be expressed as follows. We have three constraints for fairness limitation. The non-negativity constraint for the decision variable can be expressed here, x sub j equal greater than 0 for j is equal to 1 to 9. And the optimal solution, I will discuss about the process of finding optimal solution in next course, but for now, the optimal solution to the linear program is as follows. You can see that the sorghum is not optimal for cultivating in three forms. More example, consider the following problem. A company has discontinued the production of unprofitable line which has created excess capacity on some its machines. The management is now exploring the possibility of utilizing this excess capacity to product the other product, namely product 1, 2, and 3. The available capacity on machine is summarized as follows. You have 500 hour per week for milling machine, 315 hour per week for lathe machine, and 150 hour per week for grinder machine. This is the photo of these three machines, which is very common in the industry. The number of machine hours required for each unit of product are here. In this table, you can see that. And the sales department has provided the following information that is needed for writing the constraint. The sale potential for product 1 and 2 exceed the maximum production rate. So it means you don't have any limitation for producing product 1 and product 2. The selling department can sell all of them. But the sale potential for product 3 is 2 units per week. The unit profit for product 1, 2, 3 are $500 to $50, $20, and $25 respectively. And the goal is to determine how much of each product should be produced to maximize profit of the company. So, how we can formulate this problem? Let xi represent the number of units of product I produced, where I is equal to 1, 2, 3. The linear programming model for this problem can be expressed as follows. Constraint 1 pertains to milling machine's capacity. Constraint 2 pertains to the lathe machine's capacity. And constraint 3 pertains to the grinder machine capacity. And constraint 4 is a demand constraint for product number 3. And this is the optimal solution for this problem we can discuss in the next course. And you can see that x1, x2, and 3 should be produced 26 about, 54 about, and 20. And we have about $3,000 profit. Consider the following problem where the value of the C1 is uncertain. This is an example of the sensitive analysis which we discuss in the future course. In short, sensitive analysis in the linear programming involves examining how change in the model parameters such as objective function coefficient, right-hand side value, and constraint coefficient can affect the optimal solution. This helps decision maker evaluate the potential impact of change in these parameters. So we use the graphical analysis to find the optimal solution for different potential value of C1 from minus infinity plus infinity. If C is less than 0.5, we have the single objective function which is equal to z5 is equal to 5 and x star is 0.5. When C is equal to 0.5, we have the multiple solution. Any point between line between 2, 4 and 0.5, and we have the same objective function for all points between these 2 points. If C between 0.5 till 1, x star is equal to 2 and 4, and z is equal to c plus 4. Again, when we have c is equal to 1, we have the multiple objective function, and the objecting function will be 6. And if in the last one, if c is greater than 1, we have the single objecting function which is equal to 6 times c. We will discuss in the duality theory and sensitive analysis course about how we can find this optimal solution in different cases of C. Another example, consider the following example. This is very well-known example in the operation research, which is called transportation problem. A company produces medical equipment at 2 factories and has received order from the 3 medical customer. The table below shows the shipping cost per unit for each factory to each customer, as well as the number of units to be produced at each factory and the order by each customer. A decision need to be made regarding the shipping plan, or how many units should be shipped from each factory to each customer. It is called transportation problem. How we can model this problem? We have xij as a number of units shipped from 2 factories, 1 and 2, to 3 customers, 1 and 2 and 3. Our goal is minimize the shipping cost, which is represented by the objecting function, which is have here, and each customer has a certain order to fulfill. Customer 1 order 300 unit, customer 2 order 200 unit, and customer 3 order 400 unit, and output of the factory 1 is equal to 400 and output of factory 2 is equal to 500. To summarize, our model aims to minimize the shipping cost by ensuring that the total unit shipped from each factory equal to their output and the total unit shipped to each customer equal to their order as follows. And we can solve this problem with the method it's called simplex method. We will discuss in the course I think 5, and you will now how to solve this problem. This is the objective function of this problem is equal to 5440. Let's consider another example where a company wants to create a new alloy consisting of 40% tin, 35% zinc, and 25% lead. To achieve this, they have access to several available alloys that have specific properties as follows in this table. Model the problem to minimize the total production cost for producing a new alloy. To a solution, we will use xi to denote the amount of each alloy I use, where I range from 1 to 5. The company objective is to find out the optimal proportion of these alloys that can be blended at the minimum cost to create a new alloy. This problem can be formulated as follows. The first limit guarantees the amount of tins. The second limit guarantees the amount of zinc. The third limit guarantees the amount of leads. The total percentage of 5 alloys should be equal to 1, which is stated as force constraint. And we have the objective function. If we solve this model, we have the objective function like this, and we don't use the fourth and second and fifth alloy to make a new alloys. We have another example which is very well known in the industry. Let's consider the example where a logging company needs to fulfill order with a specific dimension as follow and deliver them to a respective applicant. To fulfill the order, the logging company needs to use the standard board with the dimension of the 2 times 4 times 11, where 2 represent the 2-inch and 5 represent the 5 feet. There are 5 different ways in which the standard board can be cut to prepare the order of the customer. The company's plan is to use the minimum standard board required to fulfill the order of the customer. How we can formulate this problem? Now here we have the formulation. If we use x1, x2, x3, x4, and x5 to represent the number of standard boards cut according to the one of the following possible way, the objective function can be written as follows. We have the minimization objective function, summation of the x1 to x5. Since 4 boards with the dimension of the order 1 result from the cutting of the first type, and the 2 boards with the dimension of the order 1 result from the cutting the third and the fourth type, we calculate the number of order 1 as follows. So we have 4 cuts, 2 cuts from third type, and 2 cuts from fourth cut of type. We have this limitation for order number 1. For order number 2 and order number 3, we have the similar limitation. Similarly, also we need to add the non-negativity constraint to the variable. We can summarize the model for the given problem as follows. So we are going to minimize the summation of the cut and subject of the order of the constraint and non-negativity constraint. This is the optimal value of this function. We have C star as the optimal value of the objective function. We don't know, we can solve this problem as a duality theory that we discuss in the third course of the operation research course in the future. Another example, let's consider the example of the dynamic programming. I will discuss this subject in the future course. This is a very important course. It helps us to solve the problem in the subject of the time. It's called dynamic programming. With this subject, we also calculate an objective function for the model with the uncertain parameters we will discuss in the next course. So let's back to example. A manufacturing company that has a commitment to deliver 800 fridge this year and another 1,200 next year to a chain store. The production capacity of the company is 1,800 fridge, and the estimated production cost per unit is 1,000 for the current year and 1,500 for the next year. Additionally, any unit produced this year that remained in the warehouse will incur a charge of 200. Assuming that the company has no inventory of fridge at the beginning of the contract and want to have no inventory at the end of the second year, they require a production plan that minimizes the total cost of fulfilling the contract. To arrive at a solution, we will define the decision variable as follows. T1 is production quantity for the current year. T2 is the quantity produced for next year. Q0 is the inventory at the beginning of the current year. Q1 is the balance at the end of the current year, and Q2 is the balance at the end of the next year. Since Q0 is 0 and the company wants to have no inventory at the end of the second year, Q2 is also 0. Therefore, the objective function become as follow. We are going to minimize this objective function. Inform When formulating the constraint for the problem, we need to ensure that the total inventory at the beginning of the current year plus production in the current year minus remaining inventory at the end of the year is equal to commitment made for this year, which is equal to 800. Therefore, we have this constraint in the equality form. Similarly, for the next year, we have the following constraint. Since Q0 and Q2 is equal to 0, the problem formulation can be summarized as follows. So this is the model, and you can solve the model maybe in the method of the simplex, and this is the objective function of this problem. Let's move on to another example to illustrate the various solution approach. Solve the given In part 1, solve the given problem. In part 2, convert the objective function to mean and solve it again. In part C, change the objective function to maximize here and solve it again. Change the objective function to this objective function and solve it again. Change the objective function to minimize this objective function and solve it again. Change the second constraint to an equality constraint and solve it again. And finally, change the second constraint to a greater than or equal and solve it again. Solution for part A. Since the optimal solution for the linear programming problem lies at the one of the corner of the feasible region, we can list all corner solutions and select one with the highest objective function. In this case, the model is in the form of the maximum. And then find the optimal solution. The figure and the table here show the corner point and the corresponding objective function. So you have 1, 2, 3, 4, 5, 6 corner point, and corresponding that you have also objective function. Because we are going to maximum the objective function, the optimal solution happen in point D here. Based on a figure and feasible point from part A, point A is the optimal solution in the case of the minimization. Changing the objective function to here, z is equal to x1, will result in a new objective function which is parallel to a constraint x1 is greater than 3. This will lead to a special case of the objective optimal solution where the corner point C star and F star are both optimal solutions. We have the multiple optimal solution case. By changing the optimal objective function to this function, the objective function would be E star and Z is equal to 12, which is shown in this figure. This is the optimal objective function. It happened in x1 is 0 and x2 is 6. The objective function is the same as the objective function in part D multiplied by -1. Therefore, the optimal point remains the same, which is E star, but the value of the objective function would be -12. So we have the same solution but different objective function. In part F, if the second constraint is converted to an equality constraint, instead of less than, the feasible region will be a line CD here, and the optimal point will be in D star or here, this point. We can solve this problem. And the final When the second constraint is changed to a greater than or equal, the feasible region change to this part, CGD, and the optimal point would be happen at this point, G star, with the maximum objective function. Okay, if you are really interested in practicing more exercises related to operation research, I invited you to check out my learning website, optimizationcity.com, where you can find a variety of resources and examples to help deepen your understanding of this subject, whether you are studying the linear programming, simplex method, optimization methods, and any other topics in the operation research. You will find plenty of exercise over there. Challenge yourself and reinforce your knowledge. So why not to give it a try? Let's visit our website and you can find all you need.